I'm not seeing it. All right. Let us start with the classic CW or Morse code receiver. If we go back into the dim mists of time, we come back to Edward Howard Armstrong's regenerative detector, which is like the first serious receiver. Before that, they were doing things like coherers, where you had iron filings to stick to a magnet depending upon the received signal. First real receiver was the regenerative detector. It's an interesting idea. It's an amplifier. Now, the way you make an oscillator is you take an amplifier and provide feedback. And a regenerative puts an adjustable amount of feedback till it's just on the verge of breaking into oscillation. And when a signal is received, it throws off the balance, goes into oscillation, and then you get a tone in your headset. The regenerative receiver is a fantastic receiver if there are no other signals. The selectivity is horrible. It's a mile wide, but it's dirt cheap and very sensitive. All right, next slide. In the 1920s, they developed the tuned radio frequency receiver. Now, you have a peak detector, which is a diode for AM, or you can use a regenerative detector for Morse code. And what you do is you put some amplifiers to bring up the received signal to be strong enough to be detected, and then some amplifiers to amplify the resulting audio signal to drive headset or loudspeaker. But the input stages are tuned to pick the frequency you want. You tune the input stages to the station you want. Here's the problem. If you have 3 stages of amplification, you have 3 tuning controls. And to use a TRF receiver, you're twiddling 3 dials constantly, and that's a one-way trip to the loony bin. So right there, the amplifiers make it not, you have a nice amount of gain, so you get a nice loud signal coming into the loudspeaker, but you're tuning all the time to get maximum performance. All right, next slide. The next development was the superhead or super heterodyne, which is an interesting idea. To avoid all of that tuning, let us imagine a TRF receiver that is factory tuned for 455 kilohertz. Doesn't have to be, but back in the day, that was the standard. And vendors actually sold tuned filters. All these are recognized IF cans, preset for 455 kilohertz, and typically had a proper width for an AM signal. They were too wide for CW, but perfect for AM. And it was tuned to hold for life. They're called IF cans, and it creates an IF strip. And it's followed by a detector, audio amplifier, and headphones or speaker. That's wonderful, but nobody wants to listen to 455 kilohertz. But here's the trick. In front of it is a converter. The converter is done to change the frequency of the signal you actually do want to hear to 455 kilohertz. And you now need 2 tuning adjustments that are usually mechanically connected. That if you've ever seen these old radios, they have two variable capacitors on the tuning dial. So they go together. One of them tunes the input. The other one tunes the reference oscillator. More on that in a minute. Don't freak out. But they at the factory, they're made to track together. Now let's see. Let's have the next slide. All right. I promise you, this is just high school trick. No calculus here. If you multiply two sinusoids at different frequencies, it produces sinusoids of the sum and difference frequencies. In other words, if you take two signals at different frequencies and you put them through a linear network, a linear network is if the input goes up by 2%, the output goes up by 2%. Any nonlinearity, say a diode, if the input goes up 2%, the output will not go up 2%. And that will cause the input frequency, number one, input frequency, number two, the sum of the two, and the difference of the two. And if you don't believe me, dig out your old 11th grade textbook. It's in there. Sine A times sine B basically is, sine A plus B and cosine A minus B. Now, the first frequency is the frequency you want. The second frequency is an oscillator you're tuning to be 455 kilohertz away. It's your local oscillator, and it's like a microscopic transmitter. It's just generating a signal. You run the two of them into the mixer, and then what you want to do is amplify usually the difference frequency and reject the others. Now, the input stage you have to tune. Because what happens is, remember, sum and difference. So if you think about it a minute, if you have your local oscillator here, let's, like a slide rule up and down, slide rule down. If your local oscillator is here, up 455 or down 455, they both work. So what you want to do is use an LC filter to take this one or this one and reject the other one. And any bleed through is the image. So you want to reject the image on the input stage with one tuning capacitor. The other tuning capacitor changes the reference local oscillator frequency. So if you want to receive 7.1 megahertz on 40 meter CW, the local oscillator will typically be 450 kilohertz below that. And the 455 kilohertz sharply tuned intermediate frequency filtering will get rid of all the others and process the one you want to be detected. So I gave the example here of 1,000 kilohertz will produce 455 with either 545 or 1455. We're all playing with numbers here. But the idea is the one you don't want is the image. Next slide. And as I said, the input is a preselector, which is often usually an RF amplifier, but it doesn't have to be. Use a tunable, LC circuit, inductor capacitor to select the desired input, say 545, and reject the image 1455 in the example I just gave. The local oscillator, again, is a tunable LC circuit that says frequency, which in this example is 1,000 kilohertz. And the two of them must be on the same shaft and have to track each other for smooth single knob tuning. Now, let's see. All right, let's go to the next slide. This next slide. All right. I go on about this for a while, don't I? Oh, I know what I want to say. Let me talk for a second on a little bit off topic. LC circuits. You take a pendulum and you hit it. It always swings at the same rate. Take a bell, hit it. It always rings at the same rate. It's a resonance. You take a drinking glass, tap it. It always goes ping, ting at the same rate. These are mechanical resonances. The beauty of inductors and capacitors, if you put them together, they have their own reference. If you electrically hit it, it rings like a bell. And 99% of ham radio depends on that. So if you want to select the frequency, the primary thing is an LC circuit tuned to that frequency. And I have seen some old video somewhere about some guy at Bell Labs actually gave some good examples of it where you actually see the things resonating. All right, let's see. So we're good, right? We go to the next slide. Now you get the picture. On the upper left is the antenna. All right. Then you have the tuned RF amplifier, which is the preselector that rejects the image. Then you have the mixer that mixes the input signal with the local oscillator. And the filter and the amplifier is typically 3 amplifier stages with IF cans or filters in between them, which in a classic 1930s example, when this became very popular, would be about 5 kilohertz wide, good for an AM signal. Then you have the demodulator, which is usually just a diode, which converts the 455 kilohertz down to audio. Now, I removed the section on detection, how a diode detects. Is everybody okay with that? Right. And then you go to an audio amplifier to drive your loudspeaker or your headphones. No questions? Am I doing good or are they lost? Yes. All right. Next slide. All right, right now we're in the middle of a Great Depression. Let's move up a little, maybe on the other side of World War II when things changed. Obviously, transistors changed the whole world. They made portable radios practical and allowed car radios to, run directly off the car electrical system. Anybody here remember a vacuum tube car radio with a vibrator? A little thing that generates AC by mechanic. It's like a chattering relay generating an AC signal to power, to go through a transformer. By the way, another off-topic thing. Back 120, 130 years ago, Edison was really big on direct current. Other guys, let me give you one name, Tesla and the like, were very big on AC. And it was a whole big to-do, and it's very simple. Copper is expensive, glass is cheap. If you want to build a long transmission line, you want to minimize the copper, and who cares how much glass you need for the insulators. So you want thin wires. And the way to put a lot of power in a thin wire is to go to a high voltage. Too high to run it to the house. So with AC, you generate it, you step the voltage way up, transmit it on relatively thin wires. A transformer brings it down to the house. You can't do that with DC. Today you can, but after about 120 years, maybe it's a little late. All right. Now, on the subject of AM radios, in the 50s, a big thing was ferrite antennas, which was basically a coil on a core of ferrite material would work beautifully for AM. You didn't need an external antenna. Yes, absolutely. And the biggest thing about a car radio is you want push button tuning. You do not want to have to sit there and tune. And those of you who love to work 75-meter phone from the car, please don't do it while you're driving. If you ain't tuning in an AM broadcast station while driving is bad, tuning in 75-meter SSB is suicidal when you're driving suicidal. All right. But originally, back in the day, what those push buttons would do would be select coils and or capacitors. Usually, when you turn the tuning dial, you would turn the capacitor, the button would link it to a capacitor, and you press a button and mechanically switch it over to another capacitor, and you'd link the knob to the capacitor. So when you press the button, it selected that capacitor, tuned in that station. Today, it's all done electronically. Much more reliable, much simpler, but you do what you gotta do. All right, next. Next slide. Now the next is automatic volume control, or AVC. Let me tell you a secret. Car radios move. And those of you who operate, say, 2-meter radios in the car realize they move too. And you see wide variations in received signal strength. No surprise, right? Particularly when you're just east of Route 110 on the LIE. Automatic volume control, by the way, just for sake of argument, this does not apply really for FM. It's really for AM. AVC averages the audio output. What it does is you take the signal going to the loudspeaker, and you have a little circuit that gives you an average, sound level value, somewhere around the volt or so. And this voltage feeds back to the IF amplifier where most of your signal amplification is, and it turns it down a little bit. There's a stage in there where the higher the voltage, the lower the gain. So if the output's too high, it turns it down. It's a feedback loop that more or less maintains the average value. Now keep in mind, it has to be properly done. The feedback loop has to keep a constant output as input varies. But remember, the input is varying all the time, at the sound frequency, so it can't be that fast. On the other hand, you can't be so slow that you drive under an underpass and it doesn't correct till you're out on the other side. So adjusting the time response is very important with AVC. So, like baby bear's porridge, not too fast, not too slow. But you never thought I'd use baby bear's porridge. Next slide. All right, now let's talk about HF band, 3 to 30 megahertz receivers, something that's near and dear to most of our hearts here. HF stands for high frequency. Years and years ago, some people came up with these names, and 3 to 30 ended up with high frequency, and no one's ever changed it. The beauty of HF band, it is the most intriguing part of the radio spectrum. Nowhere else in the radio spectrum can you get around the world signals, without all kinds of stuff like satellites or whatever. That ground wave will allow signals like, say, 80 meters to hug the Earth and follow the curvature of the Earth for a few hundred miles. Around 20 meters or so, you're actually bouncing them off the ionosphere, which is like about 60 miles up. At 20 meters, the ionosphere level of the atmosphere, it's kind of like, acts like a mirror, and it bounces down. Sometimes you get a double bounce. The problem with these effects is they are maddeningly variable. Some days you tune to 20 meters and all you hear is, say, Europe or Africa coming in. Some days you turn it on and you check to make sure that the receiver's working. There's nothing there. Sometimes it'll change right in the middle of a conversation. How many of us, show of hands, have had somebody just disappear on you? You turn it over and he never comes back. It's maddeningly variable, but the miracle is that it's there at all. No other part of the spectrum gives you that. Up, running away, can't take it anymore. Yeah. All right, now, HF receivers like hams use primarily have a lot in common with AM broadcast receivers, but there are some differences. And the main thing is you're now dealing with a fairly wide frequency range. Now, let's talk 1950s technology. Tuning is broken down into sub-bands. And like I mentioned with the push-button car radio, you have a rotary switch selecting the bands. You're selecting different coils and/or capacitors. Some radios tune a capacitor and you switch coils. Some you tune an inductor and you switch capacitors. Doesn't really matter which. The beauty of it, or the nightmare of it, if you ever take a look at one of those older pre-everything computerized ham radios, the band switch is this long thing that runs the entire length of the chassis with about 10 discs of switching contacts on it. So you're switching everything. And they are impressive until they stop working. Then they're a nightmare. All right, next slide. Still no questions? Should I get worried, Jerry? All right. This slide was really intended for a non-ham audience, so I think this is old hat for you guys. Obituaries on the death of CW are premature. Morse code, once used for spark transmitters. I had a nice section on spark transmitters, but George made me take it out. Blame him. Was used with CW for many years for reliable communication. You know this. Voice can be more reliable than voice with trained operators because it's a narrow band digital code. What? You call it what you want. My point is, Morse is a terrible, terrible system for automated communication. It's designed for the vagaries of the human brain. A computer, when you tell a computer a dit is 1 unit, a da is 3 units, and the space is 1 unit, and the space between letters is 3 units, I dare you to actually send that it doesn't confuse a computer completely. That's why real digital codes came out. They actually match what the computer is expecting. But from a standard, it has a lot in common with them. But it is very narrow band, which now brings up other problems. Your 455 kc IF cans are 5 kilohertz wide. That'll allow, I don't know, maybe a dozen CW signals to come through and interfere with each other in your ears. So more on that later. Now, as we all know, there is no, pretty much the world has gone away from Morse. But try going on the CW bands on field day and you realize maybe not so much. Anybody here ever worked on CW on field day? Raise your hand. That's it? All right, so I have to tell them. It's a zoo. Interesting fun fact. Every air traffic control beacon or landing system has a Morse code ID. Every pilot has to have familiarity with Morse code. Now, that doesn't mean to say you have to really copy it. You're allowed to use a cheat sheet, and a lot of pilots do. But that tells you you're on the signal you expect. It's embarrassing or worse when you're not. Oh yeah, that's the or worse. All right, next slide. Now, let's tweak our superhat design for CW. Now, remember the mixer and local oscillator up at the front end? Instead of a diode or similar detector, you do it again. You have a second mixer with its own local oscillator, also known as a BFO, beat frequency oscillator. And that is not 455 kilohertz away. That's about 700 or so hertz away, which gives you that nice Morse code tone. Sometimes you can tweak the frequency a little bit by personal preference, but you know, it's not going to be below 500. It's not going to be much above around 1100 hertz. Again, most of you guys know this. Wasn't written for you, but we'll play. But you understand, the idea is for AM, a diode will turn that 455 kilohertz signal, strip out the RF, and just give you the audio. The CW, you mix it down to 700 hertz. Now, if the receiver is tuned past the CW signal, as you come in, you actually hear the difference frequency. And then as you come in, eventually, they will actually go, the difference frequency goes to 0, and you lose it, 0 beats. Then you come out the other side. We've all heard that wee whoop sound as you go past the signal. And the idea is to tune it so you get a nice musical, about 700 hertz tone to copy Morse. And like I said, what's very important is it's two-sided. As you come in, it goes down in frequency, then you pass, so it goes up in frequency. And here's another problem. Like I said, that 5 kilohertz bandwidth is kind of wide for Morse. Next slide. So let's talk about improving IF filtering. So better filters were developed than the classic LC filter, which at 455 kilohertz gives you about 5 kilohertz bandwidth. That's not the only way to play the game. AM radios started using ceramic filters that were simpler and less expensive than those IF cans, which had to be tuned at the factory and then sealed with glue. but they're still too wide. Crystals, your old boat anchor receivers, the better ones, have a crystal filter option, which is nice and narrow. And you might even have a phasing control, so you can adjust it a little bit. It's a single, narrow fixed bandwidth. Now, keep in mind, as you're talking about crystal filters, they don't really work well at 455 kilohertz. So there's nothing sacred about 455. So you're a higher IF. And you put a crystal, you put one or more crystals in there to give you a nice narrow filter optimized for CW. So like I said, as the IFs began moving up to several megahertz. I think 9 megahertz in recent years has been very popular for that. Next slide. That's really for FM broadcasts. And they're very wide. I mean, they do have a place. There are places where you can shove a 10.7 megahertz, 200 kilohertz wide filter into another radio other than FM broadcast radio, but it's kind of a specialty art. All right, now, as communications frequencies move up, we have a problem. Remember the image. If you're in the AM broadcast band, to say 1,000 kilohertz, so the desired signal and the undesired signal are a significant percentage apart. You go up to 10 meters, 28 megahertz, it's just a few percent difference. You're not getting much filtering. So if you have an old cheap boat anchor, the higher you get, you're suffering with image rejection. So they came up with another idea. To raise the IF frequency. The problem is crystal filters are very narrow. In the technology of the 50s and early 60s, you could not build a good AM or sideband wide filter. So you had a problem. You need to go high in frequency to hold down the image, but you don't have good filters. So somebody said, I know. Remember the way we went from the TRF to the super heterodyne? And remember, for CW, we do that again with the mixing? Well, we're having fun. Let's do it again. Double conversion IF. You come in at RF, you mix it with your first local oscillator in your first mixer down to your first IF. And here's where you might want to go 10.7 megahertz, so it's 200 kilohertz, is a nice image reject bandwidth. Then you have the next mixer, local oscillator, down to 455 kilohertz, where you put in your IF filtering, and also in CW, you can actually use crystals to say 9 megahertz, 10.7 megahertz. You play around with this stuff. But the key point is you want to have a high first IF, but they didn't have good filters, so you can do all one IF. And then along comes sideband, where I think you have to go even lower. I think those Collins mechanical filters were like 250 kilohertz, if I remember right. Basically, remember the old Collins mechanical SSB filters? They were really low frequency. And if you didn't go double conversion, you had like no image rejection at all. And just for the sake of argument, I don't quite understand why you would do it for a ham radio, but you see some applications with triple conversion. I think Drake was very big on triple conversion radios. I never understood that. All right, next slide. All right. In more recent times, there have been some new developments. One of them is SAW filters, surface acoustic wave. They are very good if you want a single bandwidth. They will give you the exact bandwidth you want at a very high frequency. So now you move your IF up to like 60 megahertz, and that becomes a whole new lot of fun. But they do have their applications. And they're also fairly expensive, which is why they never really appeared in ham radios. I did work with telemetry, UHF telemetry radios for the military. I was trying to convince these people to get rid of all the stupid tank circuits and go to SAW filters, but never actually happened. All right, next slide. And here comes the biggie. Software-defined filtering. For years now, a big thing is software-defined radio. You basically set up your computer, you put in special purpose programs, you have a front end that goes into the computer, you have a setup that makes this look simple. In recent years, the ICOM IC7300, the ASUS FT891 and 991 have figured it out. They're using software-defined filter, software-defined radio technology in a more user-friendly environment. And a couple of years ago, I bought a Yaesu FT891. Just as an aside, I got my novice license in 1962. And there was some very expensive equipment there. That was pretty good. There was no way I was going to afford that. I couldn't even afford to drool over it, let alone use it. And so we had to make do, and there were a lot of problems with it. And now I see the FT891, and out of the starting gate, this is everything I would have killed for back then. It had the receiver, it has direct digital synthesis, which I'll get to, tuning. It doesn't drift. That's the bane of everybody's existence in the day. It doesn't drift. That's a miracle like the parting of the waters of the Red Sea. Also, I can select my bandwidth with a knob. I can tune a little. I can select it. I can customize my IF bandwidth to the signals I'm receiving to optimize the one I want and reject the ones I don't. I mean, this is fantastic stuff. And I'll tell you, the FT891 is something like $600. Adjusted for inflation, I couldn't buy anything. I mean, it had to be like $45 back then. I could buy a couple loose parts for $45. Just a couple, not enough to do anything. But here's my point. The bandwidths are variable and they have nice, consistent filter skirts. The young lady over there, when I talk about skirts, it has nothing to do with clothing. A filter, let's say a bandpass filter, at some frequency goes right through. At other frequencies, nothing goes through. A filter that goes from everything goes through to nothing goes through on this side and on this side is a wonderful thing. And when they invent it, let me know. So real filters have a slope. It's not a, yeah, the term is a brick wall filter. It is a fantasy. It doesn't exist. But real filters have skirts. I have a problem here. 2 hands on a microphone, kind of like this. And you want them to be reasonably sharp. But on the other hand, as you start getting near the totally vertical skirts, you start getting other problems. But the idea being, with the software-defined filtering, you have some play. And the bottom line is, are you hearing the guy you want and not the other crap? So by definition, if your answer to that question is yes, you're golden. We don't care how we got there. Next slide. I might finish this early. I was expecting questions. All right. All right, here comes the heavy part. Fasten your seatbelts. This may be a bumpy ride. You've been hearing about this for how many decades? Now I'm going to give it to you straight. Let's see if you're man enough to handle it. AM radio has a nice sound, but it's rather inefficient. A real AM signal can be 10 kilohertz wide if you want good fidelity. On the 75 meter band, some guys actually use AM, but I think they hold it down to 5 kilohertz, but still sounds okay, but it's not that real full quality audio. Can it be narrowed down? Well, the answer, like so many other things in life, is yeah, but you have to give up that nice full sound quality. Many things in life have trade-offs. All right, so let us examine the spectrum of a typical AM signal. Just for fun, let us assume the modulation is a pure 1 kilohertz tone, which obviously contains no real information. But if you whistle into a microphone, that's pretty close. So just imagine whistling into a microphone. Next slide. All right, this isn't that clear, but you see, that's a spectrum analyzer waveform. Nowadays, you can buy a spectrum analyzer that will show you something like that, from Amazon for what, about $75? Whatever the hell it is, I have one. Those things used to be thousands of dollars. And to tell you the truth, that little piece of junk I bought from Amazon is fine. Now, obviously, you're not selling equipment to the US government tested on that little Amazon thing. But you know what I'm saying. If you want to look at something with your ham radio, it's fine. Now, what it is signal amplitude versus frequency. I believe a so-called waterfall display is a variance on this idea. I usually avoid them, so I'm no expert. Some things I'm a traditionalist. So it's frequency, and in the middle, we have our RF carrier, which might be something like in the middle of 40 meter band, say 70, 50, 7.05 megahertz. And you notice the 2 little nubs on the sides. If you whistle into the microphone, those little nubs are exactly, in the case if you're really good at it, you do a 1.00 kilohertz whistle, they're exactly 1.00 kilohertz off. Now, when you stop whistling and start talking, all of the voice information is in those 2 nubs. A, they're redundant. B, you're putting most of the power into the carrier. The higher it is, the more power you transmit. Yes. absolutely true, but irrelevant. So you just get a mirror. No, I'm serious. I'm serious. That does not impact the way it sounds. You are absolutely correct, but it's not an issue. Thank God for when something isn't an issue. Enjoy it while you got it. So is everybody okay with this picture? Next slide. As I mentioned, the Centipede is a carrier at the nominal frequency. The smaller side peaks on the modulation 1 kilohertz away. The loudness of the whistle changes the height of the peaks. But, as I hinted out, but didn't hit you with, the peaks cannot exceed half the height of the carrier. What happens is, if you look at an AM signal on an oscilloscope, in other words, time is the base, not frequency, you find you get that, envelope of a sine wave, the very fine sine wave in the middle and the slow sine wave on the outside. For CW, it's just the inner sine wave. There's no variation. So the envelope is like this. Then as you start to talk, the envelope comes down. When you exceed half the power in the sidebands, they cross. And that's a no-no. It distorts. You're not going to blow up anything. It just sounds lousy. So the problem with AM is you're going to only put a small percentage of the total power into where the intelligence is. The rest of it is just going along for the ride. All right, next slide. So we have half our transmitted power in the carrier, a quarter of the transmitted power in each of two totally redundant mirror image sidebands, side peaks or sidebands. If you look in the frequency domain on the spectrum analyzer, you see what the sidebands mean. Sidebands mean nothing on an oscilloscope. And I think that's driven a lot of hams crazy over the years. They're looking at oscilloscope waveforms and say, what does this have to do with sidebands? You have to look in a frequency and a spectrum analyzer. All right. In the vernacular, that sucks. All right. How do we get rid of all the excess baggage? How do we cut this down to the core? Well, in the 1950s, the technology came along and there was a huge rush. And let's see what they did. Next slide. One thought is just passing an AM signal through a very, very narrow filter. That's where the old Collins mechanical filters came in. You can also use a 9 megahertz IF and the narrow 9 megahertz filter. The standard is 2.7 kilohertz wide, is the standard for single sideband. It gives you reasonable voice quality, and it isn't too wide. And by the way, until direct digital synthesis, there was no point in increasing the bandwidth of a single sideband signal for improved audio quality, because as we all know, single sideband audio is terrible. That has changed, by the way. I'll get to that later. So like I said, there are standardized filters, the old mechanical filters at very low frequency, the new crystal filters, with a standard 2.7 kilohertz bandwidth optimized for human voice characteristics. Now, this is the classic way. Let me have the next slide, but I may digress. All right, before I get into this, there's another way to do it, a phasing SSB detector. You're trading a mechanical filter for phase shift networks. And And I think after playing with this for a number of years, they decided 6 to 1, half dozen the other course about the same thing. Just go with the damn filters. So the phasing SSB generator does exist as a abstract, and in some cases it is the way to go for some really oddball stuff, but not for ham radio. And I believe we're here to discuss ham radio, not the other oddball stuff. All right. So what do we do? Can we throw it all? What are we throwing away? Well, despite Harry's problem, we can immediately throw away the redundant mirror image sideband. Thank you for giving me something to give you a hard time about. I appreciate that. It helps. We can throw away that unnecessary sideband. It's completely redundant, but doesn't save us very much. The problem is the carrier. We're wasting all that energy in the carrier, which is just sitting there like a lump doing nothing. What's that? More. So, what do? I know what we do. We go to the next slide. That's what we do. Now, we are transmitting just the sideband to a non-existent carrier now. We filtered out the carrier. We filtered out the sideband. All right, what do we do? There is a complicated control system that allows us to tune in an SSB signal at exactly the right frequency. This is a very, very sophisticated system, but it has an advantage. It's absolutely free. It's between your ears. It comes pre-installed on the top of your neck. You do it by listening. And off-channel single sideband signal is gibberish. Meaningless. As you bring it in, it starts to sound like humans, but distorted. As you come in from one side, it's very low in pitch. Blah, blah, blah. And then you go on the other side, very high in pitch. And there's a sweet spot that you can drive yourself completely crazy trying to nail it, where you actually start to hear something that makes sense until your LC circuit derived VFO starts to drift and it all goes to hell. Interesting comment. Neil Armstrong, July 16th, 1969. Yeah, July 20th, 1969. Remember the famous line that he screwed up? One small step for a man, a giant step for mankind. He screwed that up. But here's the point. It was kind of distorted. Why was it distorted? Well, two things. They knew the exact frequency it was operating at. It wasn't tuned. That was crystal controlled all the way. The problem is, even with fixed frequencies, using a crystal oscillator to determine all the frequencies on all ends, you couldn't really get that last little bit right that didn't change with time and temperature. Second thing, he was on the moon. What does every 3-year-old know about the moon? No, serious. It goes around the Earth. You have the dimensions are changing. When dimensions change, you get a Doppler shift. So you have the inaccuracies and the Doppler shift. And that's why it sounds bleh. It's a little off frequency. Next slide. I think I went through this already. Again, do not ever try to use single sideband for music. And also, you don't want to use big data. All right, next slide. Now, there were some halfway measures to fix this. All right, the old LC circuits are just not precise enough to get everything right and have it not change with time. Show of hands, who remembers the old Heath VF1, VFO drifting up the band? All right, but crystals are good, but a crystal gives you one frequency. You cannot tune a crystal. Well, in theory, there's a variable frequency crystal oscillator, but that's not tuning, that's tweaking. That's kind of like bending something. You're not picking it up and moving it, you know, you're bending it a little. That's a subset of bending. Only the graphite is, no, a variable control crystal oscillator will do the same thing externally and repeatedly. Basically, you put a capacitor across the crystal, and if you do it right, you can tweak it a little. But going with the pencil on the crystal blank, kind of the same. Yeah. Yeah, you change the mechanical resonance across the, yeah.
To generate a reference frequency, and then you had a frequency counter that would open up for a period of time, and you'd count the frequency that it was transmitting it at, and then adjust the transmission frequency with a voltage controlled capacitor to bring it up or down, to bring it back to matching your reference frequency.
I have an answer for you. 29. That's the slide where I discussed that. But you're absolutely right. You're just premature. I haven't gotten there yet. All right, now, there are some games you can play. You can get better inductors and capacitors that are more stable. They're significantly more money, but if you're spending a lot of money for a radio and you want to throw it out the window because it's drifting, you know, maybe it's money well spent. Spend a little more money and have it drift less. But they're only a partial, they're an improvement. If some outfits like Collins Radio used to get it pretty good, and they charge royally for that. Now, there's another one. When you're playing with double and triple conversion receivers, you have one tuning oscillator. The others are fixed, crystal controlled. And that's where you put the money. In the tunable linear master oscillator. A classic approach was heresy. You take a high quality inductor with a ferrite core, and the tuning dial screws the ferrite core in and out of the coil. And that's a mechanical kludge, but it's very stable, called the permeability tuned oscillator. All right, next slide. So we want to get crystal stability, yet adjustable tuning. That's the holy grail. So here are some options. One option is the phase lock loop synthesizer. Feel better, Harry? And there's a picture coming up. Now, this works especially well with channelized receivers. Has anyone here ever heard of a radio where you adjust channels? Say 15 kilohertz steps? No, me either. You're new. You know what we're talking about? 2-meter radios are exactly that. I find a little sarcasm helps sometimes. By the way, totally aside, I do a lot of stuff with the Boy Scouts. And I find what works very well with teenagers is non-nasty sarcasm. That gets through. But if it's nasty, it always gets through, all right, you never see him again. But teenage boys especially have a sarcastic bent. And if it's not threatening, they just lock right into it. All right, so let's say, because this was not for a ham radio environment, I said 25 kilohertz, because air traffic control is done in 25 kilohertz segments. So any pilots have 25 kilohertz drilled into their skull, even more than 2-meter operators have 15. So we have a crystal oscillator. We send its output to a digital frequency divider. Let me go off topic for a minute. Those of us know that you can use a transmitter stage of a frequency doubler or tripler, which dates back to what I said before about a mixer. You get the sum and difference. If you put one signal into a nonlinear circuit, it mixes with itself and gives you sum and difference frequencies. The difference is easy, it's 0, but the sum is twice and 3 times. You can play with it. So you can use an amplifier that's nonlinear to generate harmonics and go up. When they came up with digital circuits, they found if you have a counter that counts cycles going in, that's frequency division. If you have, when the earliest digital circuits was the flip-flop, you're putting a pulse that changes, putting a pulse that changes back, putting a pulse that changes. You link up 8 flip-flops. The output is exactly 1/256, the input frequency, and it's a nice clean square wave. That's a digital frequency divider. Before the days of digital circuits, that's a huh? I can tell you exactly, 1968. I was there. I started at my first job out of college, and that was my job, designing things like that. And I said, hey, this is great stuff. All right, so what we want is our spacing frequency. If you're building an aircraft radio, 25 kilohertz. If you're building a 2-meter radio, 15 kilohertz. Now what you do is you have a standard LC oscillator. You have an LC oscillator running at the desired frequency for your radio. And you feed that into a digital divider. However, this digital divider, you can tweak the number. You can divide it by any integer. It's a much more complicated circuit than the other one, but it's not that big a deal beyond the scope of this conversation. But yeah, so you have a crystal to a fixed divider to 25 or 15 kilohertz. You have an oscillator, which is actually going to be the core for your transmitter, going through a variable counter to 25. And what you need, one dot up from bottom, little point, a phase frequency comparator compares the two signals and generates an error voltage. A phase frequency comparator is a fairly sophisticated circuit, but it's not that bad, that takes the two signals If one is higher frequency than the other, it gives you one voltage, logic 1. If it's the other way, it gives you logic 0. And you start to sweep up or down the frequency. Then when the frequencies line up, a good filter also does a phase match. And yes, you can do both. And it lines up. So the two of them are not only the same frequency, they're actually totally coincident in phase match. And it's a fairly simple circuit once you look into it. At first, it sounds really daunting, but it's really not bad. And then what you do is you have a proper filter and a ramp generator that goes to control voltage, diodes. Good time? All right. Diodes run backwards, have a capacitance. There is a way to electrically tune an oscillator with a so-called varicap diode, which is designed to have an effective capacitance as a function of the voltage. So as you turn the dial or the circuit generates it, you're tuning your oscillator. So you're electrically tuning the oscillator, and the whole thing is this big feedback loop that drives the nullity error, and then you're outputting on exactly your reference frequency times the number of the variable divider, which hopefully is what you want for that channel. And you change the divider by 1 count. You move up or down in frequency by 15 or 25 kilohertz. Now, keep in mind, it takes a fair amount of careful design to get a phase lock loop to actually lock up. But we seem to have gotten that right. Back when they were first designing these, I can only imagine how much gnashing of teeth and hair pulling there was. But it's true. I mean, we have feedback systems all over the place. Power steering is a feedback system. We take it for granted. I got a job for you. Find an empty parking lot. Go backwards. Go backwards as fast as you feel safe. You'll lose control of the car because the feedback loop is not stable. That was an interesting experiment. So maybe what they do in the movies, maybe not so much. All right, next slide. Here's the picture. Feel better? There should be no surprise here, but let's see. Where am I going to start? Upper left-hand corner, F1. By the way, I got this off the end. I didn't draw this up. I found it on the internet. I said, good enough. Engineering is the art of deciding what's good enough. F1 is the divided down from a crystal oscillator clock frequency. Let's jump to the one box from the right, voltage controlled oscillator. It goes through an output converter. I'm not 100% sure what the guy who drew this up had in mind, but we'll go with it. And that's your output frequency. You sample the output frequency, and that divide by n is not optional. Well, it can be in some cases. You don't always want to play this. Sometimes a phase lock loop is just one frequency all the time. Then you're okay. But you have that variable divider that comes to the phase frequency detector, the charge pump, the low pass filter, the bias generator are all one particular way of getting the error to drive the voltage controlled oscillator in the right direction to close the feedback loop. And when the loop closes, you have exactly the frequency you want, and you have a phase match to a signal you couldn't care less about. But the beauty of having a phase match, if the phase drifts, that actually is a frequency shift. So you don't want the frequency wobbling with the phase. Phase and frequency are intimately related. You can't change one without changing the other. So by matching the phase, you really lock in the frequency. All right, next slide. All right, we're going to finish up with direct digital synthesis. This is my favorite. I think I've said several times, the bane of my ham radio existence on HF has been things drift. Another bane is tuning in single sideband is a nightmare. In recent years, I say recent years, I mean like 10 years, it's just starting to come out now in ham rigs. And this is why I am passionately in love with my FT891. Direct digital synthesis finally allows true crystal stability. And here's the key point. Unlike a phase lock loop, seamlessly small frequency steps. You get 1 hertz tuning. You might say, why do I want 1 hertz tuning? I have an answer. Patience. Now, these were around for a while, but the cost and size and everything were ridiculous. So it's only in recent years they became suitable to add them into ham radios. But I am not going to get into the way they work, because I'm pretty good at this crap and I can't figure it out. So I wouldn't want to subject yourself to what I think it is. So let's have an idea. Why I picked this frequency, I have no idea. Let's say you want to call CQ on the 15 meter band. With DDS, here's what you do. Let's say you pick 21.267, which, to tell you the truth, I haven't been on 15 so long, I'm not even sure that's legal, but you get the idea. But notice the last 2 digits, all zeros. You have to fiddle the tuning dial to get all those zeros, because it really, it's really, talk about fine motor control with your fingers. When you get a 00, now you call CQ. Now, let's say someone else has done this, and now you're tuning an SSB signal in, and he sounds like, let's say you're at 21.2672. Just for fun, tune it to 267 even. And if he did what I think he's doing, and you do what I'm telling you to do, you get beautiful audio. It's the best single sideband audio I've ever heard in my life. It's like AM, because you're actually on frequency. I think that's it. Am I right? Next slide. Let's try the next one. George, do I have time or should I stop here? This is just a detail. Good, stop me. This is just details. Everybody happy? All right. What do I do now with the microphone? All right. I don't know. I told them. Yeah, I can. Yeah, fill the skirts.
At some point, you get the skirt narrow enough and you start going into ringing.
Yes.
What is that, and how do we control it?
Let me go back to my comment. If you take an LC tank circuit, no, let's back up. Let's back up. You take a bell and you hit it. It rings. You take an LC circuit, you hit it with a sharp pulse. It rings just like a bell. You take a narrow filter and hit it with anything, it rings like a bell. When your filter is too tight, it rings. The idea is you want your filter to be wide enough you don't get that ring effect. What it is, if it's so narrow, even after the input stops, it keeps on going, much like a bell. It becomes an electronic, it becomes an equivalent of a bell ring. And that's why they say it rings, yes.
They would go, ring.
That was simple microphonics. What happens is as pieces shake, particularly the frequency determining coils and capacitors, their inductance and capacitance will change. And what you're actually doing is acting like you're taking the tuning dial and going like this. Any other questions? George? I'm not getting any more questions and nobody's snoring. What do I do?
Thank you, Ed. I think a lot of us know a lot more about receivers now than we did.